and welcome to part 4 of revising for the specialist exam. Now, I've travelled all around Australia, I've read all of their past papers, and I'm going to show you some questions that wouldn't look out of place on a Queensland external specialist paper. Let's get going. Okay, we're in Victoria, 2006. Now, I'm excited to show you the solution to this to make sure that we can use our calculator correctly, but have a crack at it first, I'll come back. Alright, I'm going to solve this in 3, 2, 1, let's do it. So it's all about the dot product here, right? So u dot v can be found in two different ways. Now I've just written these up as column vectors, so I plus j is 1, 1, 0, and I plus 2j plus 3k is 1, 2, 2. So finding this dot product is equal to 1 times 1, which is 1, 1, plus 1 times 2, which is 2, plus 0 times 2, which is 0. So the dot product is equal to 3. But there's another way to find the dot product, which is the dot product is equal to the magnitude of u times the magnitude of v times the angle between them. So we know that the dot product is equal to 3. We can find the magnitude of that easily enough. It's equal to root 2, and we can find, it's equal to root 2, and we can find the magnitude of this, which is 3. Cos theta. Now if we rearrange that, we get 1 on root 2 equals cos theta, and we can say that theta is equal to the inverse of that 1 on root 2, and you should know that that means that theta is equal to 45 degrees, which makes my answer B. Now this is all nonsense, right? Because this is a tech active paper, I should have been able to do it differently. And so the way that I'm going to do it with my calculator is by picking up the action here and rearranging this formula a little bit. U dot V over the magnitude of U times the magnitude of V inverse cos will equal theta. Okay, you may have been taught this formula before, you may not have, but it's a nice little rearrangement of the two different ways to calculate the dot product. Okay, now we should be able to just shove that into our calculator, no thinking. So the first thing I'm going to do is put my two vectors into my calculator. So I'm going to add them in as matrices with 1 row and 3 columns like this, 1, 1, 0. So that's my u vector there. So I'm going to add that as a variable, so control, I'm going to store it as the vector u. And no surprises here, I'm going to store this one as v. Now while I think about it, I'm trying to get to degrees, so I better be in degrees mode. And so now I can take this formula that we just generated and do the whole thing on my calculator. So we're going to do some trig, we're going to do an inverse one, we're going to do a fraction. Now we're going to do the dot product of u and v. So I'm going to go up to here, vectors, and I'm going to look for vector, and I'm looking for a dot product. So I'm going to do the dot product of u and v. And then down here, I'm going to go back into my menu, back into my vectors, and I'm going to be looking for norms. If I find a norm, that's going to be finding the magnitude. So I'm going to find the magnitude of u by doing norm u, and then I'm going to multiply it by, back in here, the norm of v. Okay, and then let's cross our fingers. Alright, and we get an angle of 45, which is what we thought it was. Now, which of these ways is faster? Because just because it's a tech active paper doesn't mean that you have to do it. So which way is faster, but also which way is more accurate? I would suggest that it depends on how good an operator you are on your calculator as to whether you choose to do it this way or you choose to do it this way. But having these skills, like being able to do the dot product on your calculator, being able to store vectors on your calculator, being able to find the magnitudes of vectors on your calculator, will come in handy, not just for questions like these, but more complicated questions further down the road. So I encourage you to make sure that you've got your calculator at hand at all times, practicing those things. Alright, that's enough on that one. On to question 4. Alright, so give yourself 90 seconds to do this. Remember, this is tech active, so you want to be using your calculator if you can. Alright, I'm going to solve this in 3, 2, 1. Let's do it. I'm going to do something a bit different here. I'm going to show you the working. I'm just going to flash up the working if I didn't have my calculator. Alright, so I multiplied by a conjugate conjugate, top and bottom, simplified that, and then I get 11 over 5 minus 2 on 5i, and the imaginary component of that is just negative 2 on 5. It's not negative 2 on 5i, it's just negative 2 on 5. Now, if this was on a tech-free paper, and it certainly could be, this is what I would be doing. But we found this on a tech-active paper, so how are we going to approach it? So here we go, I'm back on my calculator. We're going to go menu, and where are we going to go? We're going to go number, complex number tools, and we're going to be looking for an imaginary part. Now, what are we looking for an imaginary part of? Of that thing there. So then we just type it in. 3 plus 4. Let's find I. It's always hiding from me. It must be in this pi area. 3 plus 4i. And 1 plus 2. Back in the pi area. I. Close that up. And we get negative 2 on 5. This time it feels a little more clear-cut to me. If I have a choice between typing that into my calculator and doing this by hand, I think I'm choosing this every time. The trick is knowing that that actually exists on your calculator. So I definitely encourage you to spend half an hour playing with your calculator, going into the menus, looking at number and seeing what it does. You can see some number tools here. What does that do? Nothing super interesting for you here. Complex number tools, there are some quite interesting things here that you can play with when it comes to complex numbers. For example, this question might not have asked for the imaginary part, it might have asked for the conjugate. And you can see we have a complex conjugate button right there. In most part, when it's just a simple conjugate, it doesn't make sense to use that, but when you've got something a bit more complicated and you want that, being able to just type it straight in makes your life so much easier. So invest the time, go through all of the menus, play about with your calculator, make it spit out numbers, learn something new. Alright, let's move on to short response. Alright, we're in Western Australia just last year. 6 marks, so about 9 minutes on the clock. Have a crack at it. Alright, and I'm going to solve it in 3, 2, 1, let's go. So we've got some simple harmonic motion going on here. So we know that the displacement, or the horizontal displacement of this thing, is equal to A cos nt. Now n's got something to do with the period, and a's got something to do with the amplitude of this periodic graph. Now n here, remember that period equals 2 pi over b, but in this case b is not b, b is n. And we're told that the period of motion is exactly 60 seconds. It takes 60 seconds for the Ferris wheel to get all the way around. So our period is equal to 60, which means that n is equal to 2 pi on 60, which is pi on 30. So I know what n is. Now, what's this a value? Now, I'm not told what the, I guess, height of this Ferris wheel is. I'm not told how wide this Ferris wheel is. It's a circle, so obviously wide and height are the same. We're talking about horizontal displacement, so the thing moving back and forth horizontally. So I don't know that yet, but I do know that its maximum horizontal speed is pi on 2. So if I knew a velocity function, I could work with that. Now the velocity function is going to be the derivative of the displacement function. So it's going to be negative. Bring the pi on 30, the derivative out the front. So pi on 30a, the cos becomes a sine, and the stuff in the brackets remains the same. So now I have a velocity function. And I know that the maximum horizontal speed, the maximum of our velocity, is pi on 2. Now what part of this function tells us the maximum velocity or the maximum speed? It's this part right here that's going to tell us our maximum speed. Picture tells 1,000 words, or whatever the phrase is. So we've got a periodic function here with no vertical displacement. So it looks like that. Now this point here and this point here is pi on 30a. And this point here is negative pi on 30a, right? So if we want to find out our maximum horizontal speed, we've got this little expression here. Pi on 30a equals pi on 2. Because this maximum velocity, which I'm calling pi on 30a, is also pi on 2. In other words, pi on 30a is equal to pi on 2. Okay, a equals, rearranging that, you get a equals 15. So, finishing all of this off, determine the values of a and n. N equals pi on 30 and a equals 15. It doesn't ask for it, but we can write the function as 15 cos pi on 30 t. Alright, so part B, and I think it's time to break out our calculator here. So it says determine the horizontal acceleration correct to the nearest 0.001 meters per second squared when the horizontal displacement is 10 meters. So first step is the second part. I'm going to find out when the horizontal displacement is 10 meters. So 10 is equal to 15 cos pi on 30 t. Okay, and let's n solve that or graph that on our calculator. So I've graphed the left-hand side and the right-hand side of that equation. I've found an intersection point, and it's at 8.0316. So that's the time at which the horizontal displacement is 10 meters. Now, it's at this stage that you might be confused about why I'm choosing this point as opposed to this point, and you might be thinking, won't it matter about the acceleration? I invite you to test this out for yourself. If you find the second derivative and graph that, you'll find that this time here and this time here, the acceleration is actually different. The object is moving in different directions, but it's accelerating at in the same amount and in the same direction both times. In a few minutes, once I've finished solving it this way, I'm going to solve it in a second way. And when you see it solved that second way, I think it'll become a bit more clear. Now, if you are screaming at your screen because you think I'm doing this wrong, I will show you how to do it a different way that you might have been taught. So, that I taught you. Alright, let's go. So we're going to do some calculus. We're going to do numerical derivative at a point. We're going to do the second derivative. The variable is x and the value is 8.0316. Okay, and then we're finding the second derivative of the displacement function. So I'm going to type in my displacement function, and I get an answer there of negative 0.10966. Alright, so I'll let my screenshot double as my working out here. The second derivative of that at 8.0316. Solve that, and we get an acceleration of negative 0.1097. Now, when I said you might be screaming at your screen, it's because this is simple harmonic motion, and if you go to your formula sheet, you'll see something that looks like this. That's pretty useful, and it can be applied to the question that we're doing right here. So it says that the acceleration of simple harmonic motion is equal to that if this is true or this is true. And if you look at the equation that we've been dealing with, yes, we have an A value, yes, we have an omega value, and we don't have one of these, but we do, it's just 0. So, now that we have a displacement function, we can easily use this formula to find that second derivative. So the question was, determine the horizontal acceleration when the horizontal displacement is 10 meters. Using this formula, we have the second derivative, dt squared, is equal to negative gamma squared displacement. Okay, so what do we know? Omega. Negative omega squared. So we have omega. Where's our omega? Omega is this here, negative pi on 30. So we have negative pi on 30 squared times that displacement. But we know the displacement, right? We were told the displacement, horizontal displacement, is 10 meters. Alright, and so we're going to have this negative here, we're going to square that, and then we're going to multiply it by 10. So, not exactly surprising here, we get this answer here. Alright, so you can see this working out is a little more efficient than this working out right here. Either one's fine. This second one is probably like the more math specialist-y way to do it. A maths method student could do something a little bit like this. You couldn't get marked down for doing something like this. So I'm happy with either. So that's question 13 done. On to question 14. So last question for this video comes from Western Australia back in 2020. Give this one a try. It's worth 4 marks, so about 6 minutes. Okay, so I'm going to solve this in 3, 2, 1, let's go. So z to the 4 equals 8 root 3 plus 8i. We're trying to find the exact solutions between negative pi and pi. Now, when I think about finding the nth root of a complex number, I think about being in polar form. So if z to the 4 equals this, we should convert that to polar form. Now, you can do that by hand, or you can come into your calculator and type 8 root 3 plus 8i, and then you can say menu, number, complex number tools, and you can convert it to polar form. Watch what it looks like when we do that. Okay, 16 and an angle of 30 degrees. Now this is where you need to be a little bit careful, right? Because we're doing this r-cis theta between negative pi and pi. So we're not supposed to be working in degrees. Luckily, it's a nice degree here, 30 degrees. So we know straight away it's 16 cis, and 30 degrees is pi on 6. Okay, so z to the 4 equals 16 cis pi on 6. Now, I like to draw things, so I know that I've got some big thing out here with a length of 16 and an angle there of 30 degrees. Now, if I'm taking the 4th root of that, what I'm going to do is take the distance from there to there and shrink it down by taking the 4th root of it. Okay, so if z to the 4 equals 16 cis pi on 6, I'm just going to move over to here with my working out. Then z equals 16 to the power of 1/4, the 4th root of 16, and then cis pi on 6 times 1/4, or divided by 4. So what I'm doing is shrinking this down all the way down to here by taking the 4th root of 16, so that's the number 2, and then I'm dividing this angle by 4. So that's 2 cis pi on 6 times 1/4 is pi on 24. Okay, so that, if you like, is Z1. And there's going to be 4 solutions. So the first solution is here, with a length of 2 and an angle there of pi on 24. Now the other 3 solutions are going to be equally spaced around this circle. That's why I drew a circle. So I've got one solution there, I've got one solution there, straight line across, and I've got one solution there. So they're my 3 other solutions to this. So I've got Z2, I've got Z3, and I've got Z4. So Z2, they've all got the same magnitudes, 2, 2, and 2. Cis, cis, and cis. And this first one's going to be pi on 24 plus this angle here, which is pi on 2. This next angle is going to be pi on 24, so starting angle right here, and then add 180 degrees on it, or pi radians. And then this last angle here is going to be pi on 24 plus 3 pi on 2, or if you want, minus pi on 2. Let's go with minus pi on 2 for reasons that will become obvious pretty soon. Okay, so I've got my 3 solutions here. I wish I'd spread them out a little more. Okay, so fixing that up a little bit. Okay, so this first one here is 2 cis pi on 24 plus pi on 2. We sort of need equal denominators, right? So this is pi on 2. That's the same as 12 pi on 24. So I'm going to have pi on 24 plus 12 pi on 24 is 13 pi on 24. 13 pi on 24. So there's my second answer. This next one here is pi on 24 plus pi. So I need them to have the same denominators, so that's going to be pi on 24 plus 24 pi on 24. So that's going to be an answer of, let's fix this up. That's going to be an answer of 2 cis 25 pi on 24. But I don't like that because my arguments are supposed to be between negative pi and pi. And you can see that solution there, the one I'm doing right now, is right there. So 25 pi on 4. I make my life a little bit easier if I do a subtraction there, because then this comes out to be negative 23 pi on 24. Alright, that brings us down to our last question here. So pi on 24 minus pi on 12. We'll just do it up here. Pi on 24 minus 12 pi on 24 equals pi minus 12 pi is minus 11 pi on 24. And that, let's see what we've got. Solve the equation giving exact solutions. I have 1, 2, 3, 4 solutions there. Now, if you don't like this kind of geometric thinking that I'm doing here, and you'd much prefer to have some kind of formula that you can just plug this into, we have the actual answers given to us by the Western Australian people. So this first part here is them converting from Cartesian form to polar form. I used my calculator to do that, and you can do that too. Or you can find the magnitude by hand here, and you can find the angle using tan theta. And then they do this solution here using this formula. 16 1 to the power of 1/4, which is what I did. And then cis, and then they add this 2 pi k on the end, where k is 0, 1, 2, and 3. You're still going to know that there's 4 solutions, but you start at the 0th solution instead of the first solution like I did. And then you sub 0 in for k, 1 for k, 2 for k, and 3 for k, and it spits out these neat little answers for you. Now, the reason I don't choose to do it this way is because I think understanding this geometry is important. Because when it comes to like complex unfamiliar questions and things like that, a lot of those complex unfamiliar questions for the nth root of a complex number rely on understanding what that picture looks like. So that's how I always tend to think about these things. That said, there are times when this formula is useful, so you should still have it in your back pocket. Okay, let's check some of this stuff off. Bam, bam, 2 multiple choices and 2 short responses. Okay, that brings us to the end of video 4. I hope you saw some stuff that maybe you didn't know about or just like had forgotten about it because you learnt it way back when. Keep practicing, keep playing with this stuff. Still plenty of time.